Good morning, everybody. Hope you're all healthy and safe at home. So let us continue with our section 9.8, line integrals. So in the previous class, we had discussed about definite integral. We are very familiar with it, how to find the integral over a particular interval. Now we are going to introduce how to find the integral of a given function over a smooth curve. Okay, now let us see how we can do it. Now, in the definite integral, what we did was we had partitioned the given interval into sub-intervals and formed the sum, and we took the product f of xk into delta xk, and then summation and tending norm p tends to 0, we obtained the integral, definite integral. Okay, in finding line integrals in a plane also, that is, we will be given any curve. Okay, corresponding to that also we have to do same as we had done in the case of definite integrals, except that instead of partitioning the interval, what we are going to do is we are going to partition the curve into sub arcs. Okay, so we are asked to find the line integral in a plane. So we will consider a curve which is there in the plane, and we will partition that curve into sub arcs and form the summation and all. So let us see, if z is equal to g of xy be defined in some region that contains the smooth curve C defined by x is equal to f of t and y is equal to g of t, where t varies from a to b. So first we are considering two parameter case, that is z is equal to g of xy is defined in some region, and we have a smooth curve in that region C, which is given by the parameterization x is equal to f of t and y is equal to g of t, where t varies from a to b. So just like we had partitioned the interval in case of definite integral, here we will partition the given curve into subarcs and form the sum. So let us see how it is, how it can be done in your textbook. The picture will be much more clearer. We will first of all we will consider any smooth curve which is given to us, and then we will define the corresponding line integral. So here we have partitioned, or we have divided the curve C into many sub arcs, and here we are dividing it into n sub arcs, and each sub arc will have length delta sk. S was the arc length, so each sub arc will have length delta sk, and the partition is like t dot is less than t1, less than t2, etc., less than tn, where t dot is a and tn is b. Just like in definite integral, we had partitioned x dot is a and xn is b, and we had partitioned it x dot, x1, x2 with this inequality. What we are considering is we are considering the projection of each sub arc onto the x y axis correspondingly, and we will form the sums delta xk and delta yk. We can also form the length delta sk also. And similarly, if P is this corresponding partition, norm P will be the partition of the length of the longest sub arc. In definite integral, it was sub-interval, length of the longest sub-interval. Here, it will be the length of the longest sub-arc. And we will choose any point on each sub-arc, and we will form the following sums. Summation k equal to 1 to n, g of xk star comma yk star into delta sk, and summation k equal to 1 to n, g of xk star comma yk star into delta yk. Also, summation k equal to 1 to n, g of xk star comma yk star into delta sk. So you can just take some time and just compare the line integral, the summation we have chosen in this case, and the sum that we had formed in the case of definite integral. Both will be similar, except that there is more than one variable in this case, and there we had partitioned the interval, and here we are dividing the arc into sub arcs. Now let us see the definition line integrals in a plane, we can see that if g is a function of two variables x and y, which is defined on a region of the plane containing a smooth curve c, then the line integral of g along c from point A to B with respect to x is integral over c g of xy dx will be equal to limit norm p tends to 0 summation k equal to 1 to n g of xk star comma yk star into delta s xk. And the line integral of g along the curve c from A to B with respect to y will be integral over c g of xy dy, which is equal to limit norm p tends to 0 summation k equal to 1 to n g of xk star comma yk star into delta yk. And also the line integral of g along c from A to B with respect to the arc length will be integral over c g of xy ds, which is equal to limit norm p tends to 0 summation k equal to 1 to n g of xk star yk star into delta s k. So this is the integral over any curve along any curve which is given to us. So we must just keep in mind that the function is defined in a region and we are considering a smooth curve. We are finding the integral of that function over a smooth curve. So we can do it. How can we do it? We can do it by partitioning the curve into sub-arcs and forming individual sums and limiting the value of norm p. We will to 0. We will get the integral. So the same concept is as that of definite integral itself, except that there is more than we are considering functions of two variables. So we can just take some time. You guys can just compare it with the line integral that we had done, the definite integral which we had done. So this is how we are going to find the line integral of a smooth curve or line integral of a region or of a surface that is given to us over along any smooth curve. So you can see that for the evaluation purpose, that is to actually calculate the integral, we will be using much simpler formulas or simpler methods. We won't use the actual formulas that we had just now derived. That is, geometrically we had derived the integral over any curve. So we can we know that any curve can be defined in two ways. That is by using the parametric equations, that is by parameterization, or using any explicit function. So either we will define a curve and we will give the corresponding parametric equations, or we will define that curve like y is equal to f of x in that formula, in that form. So in both these ways we have different ways of evaluating our integral. So let us see how we can do it. First is if the curve given to us is defined parametrically, okay, if c is defined by x is equal to f of t and y is equal to g of t, where a less than equal to t less than equal to b, then what will be integral over c g of x comma y dx. What can we do? We will replace the value of x and y by f of t and g of t. Now if x is f of t, what will be dx? Dx will be f dash of t dt, right? So we will replace this whole term in terms of only t. Okay, that will be t is varying from a to b, so this integral over c g of xy dx will be integral a to b g of f of t comma g of t into f dash of t dt, because instead of dx we have to differentiate this equation, that will be f dash of t into dt. So what will be integral over c g of xy dy? It will be integral a to b g of f of t comma g of t into g dash of t dt, because y is g of t, so dy will be g dash of t into dt. And similarly, we can find the integral along the curve with respect to the arc length. What will it be? It will be integral a to b g of f of t into g of t. And what will be ds? ds will be nothing but root of f dash of t square plus g dash of t square into dt. Okay. So I hope it is clear for you people. What we have to do here is we have to we had in the previous slide we had seen the formula in terms of summation, but that is not actually easy to for calculation purpose or for problem solving. That formula is not so easy, so we will be using these three formulas for finding the integral along the curve when the curve is defined parametrically. Okay. So I hope it is clear. What we are doing is we are just replacing x, y, dx, dy, ds and all in terms of functions of t, and the variation of t is given to us, so the integral will be from the variation which is given to us. So that is how we will find the integral along the curve when the curve is defined parametrically. Now let us see what will happen if the curve is defined using an explicit function. See, that is, suppose the curve given to us is defined by y is equal to, say, some function f of x, where x varies from a to b. Then what will be the integral value? Integral over c g of xy dx will be x. Will write all the terms. We'll replace wherever there is y, we'll replace it by f of x, and what will be dy will be f dash of x into dx. So we will convert everything, we will consider everything in terms of x only, and we will do the integration from a to b. So integral over c g of x comma y dx will be integral a to b g of x comma f of x into dx. Here dx, there is no change. Now second one, integral over c g of x comma y dy will be integral a to b g of x comma f of x into dy is f dash of x dx. And similarly we can find the integral with respect to arc length. Integral over c g of x comma y ds will be equal to integral a to b g of x comma f of x into root of f dash of x square plus 1 into dx. Here it is t, but it is x. Okay, f dash of x square plus 1 into dx. So this is how we will find the integral of a function along the curve when the curve is defined by any explicit function. So I hope that concept is clear for you guys. You just have to remember these formulas. That is how we can solve it. Using a parametric when the curve is defined parametrically and when the curve is defined using any explicit function. So to make it more clear, let us just see an example how to evaluate the line integral. Here is the example 1, that is we have to find integral over c xy square dx, integral over c xy square dy, and integral over c xy square ds on the quarter circle. That is, we are just taking 1/4 of a circle. You can see figure 9.8.4, which is defined by, the curve is defined by, okay, c is defined by x is equal to 4 cos t, y is equal to 4 sin t, and the variation of t is given from 0 to pi by 2. So what we have to do, we have to replace x, y and dx, dy, everything by in terms of t. Okay, so you can see, let us see the first part, that is we have to calculate integral over c x y square into dx. Now what is x? X is 4 cos t, y is 4 sin t, and what will be dx when x is 4 cos t? What is derivative of 4 cos t? It will be minus 4 sin t into dt. So when you are derivating this, don't forget to write the dt part, otherwise we will not know with respect to what we are going to integrate. So what will be integral over c x y square dx be? The variation of t, that is integral 0 to pi by 2 4 cos t 16 sin square t, that is y square. Square of 4 sin t is 16 sin square t into minus 4 sin t dt, that is dx will be replaced by minus 4 sin t into dt. So you can take the constants out, that is 16 into 16, that is minus 256, integral 0 to pi by 2 into sin cube t into cos t. So how will we integrate this? We will substitute by substitution, right? We will substitute u is equal to sin t. So what is the differentiation? So we'll replace this by du will be equal to, if u is sin t, what will be du? Du will be cos t into dt. So from that we'll substitute the value. I hope you guys will be recalling the integration part, how to do it with respect to by substitution method. So by substitution we will get this integral value is nothing but sine raised to 4t by 4. So what will be the value from 0 to pi by 2? Sine 0 is always 0, and what will be sine pi by 2? That is 1. So we get minus 256 by 4, and that will be equal to minus 64. Now what is the b part? That is we have to find integral over c x y square dy. So x is 4 cos t, y is 4 sin t, so y square will be 16 sin square t. Now if y is 4 sin t, what will be dy? Dy will be 4 cos t into dt. So we get 4 cos t dt. So what will we have? We can see that this is again it will be 256 integral 0 to pi by 2 sin square t cos square t dt. So how can we solve this? Here we cannot do it by previous method by substitution, because one cos will again be remaining. So here we will use the identity of sin 2t. We know what is sin 2t. Sin 2t is nothing but 2 sin t cos t. So what will be sin 2t square? Sin 2t square will be 2 sin t cos t whole square, that is 4 sin square t cos square t. So what will be sin square t cos square t? That will be sin square 2t by 4. Okay, just use the identity sin 2t is equal to 2 sin t cos t. So you can solve, you will get this. This is equal to this. Now when we have sin square 2t, we know what is sin square 2t. That is nothing but, again here also we are using trigonometric identity. We are using the formula of cos 2t is equal to cos square t minus sin square t. So this value will be 1 by 2 into 1 minus cos 4t dt, and we will take this 1 by 4 common, so that will be 64. Okay, 4 and 256 will get cancelled and we will get 64. 64 integral 0 to pi by 2 1 by 2 into 1 minus cos 4t into dt. Now this we can integrate because what is integral of 1? That is t. What is integral of cos 40? Integral of cos 40 is sin 40 by 4. And when we substitute the points 0 and pi by 2, we will get the answer to be 16 pi. So I hope it's clear. So just refresh all the integral trigonometric identities and the method of integration and all, because we are going to use them a lot. And the last one is integral over c x y square ds with respect to ds. What is the formula? It will be integral 0 to pi by 2, x is 4 cos t, y square is 16 sin square t, and instead of ds we'll have root of f dash of t square plus g dash of t square into dt, right? Now what is f of t is 4 cos t. What is f dash of t? That will be minus 16 sin square t. And here also we'll have 16 cos square t. So the root will be, that is f dash will be minus 4 sin t and g dash will be 4 cos t. So taking this square we'll get 16 cos square t plus 16 sin square t. Cos square t plus sin square t is 1 and root of 16 is 4. So we get 256 integral 0 to pi by 2 sin square t cos t dt. Here again we can use the method of substitution and you will get the answer. So this is how we can solve the problems in which we are given the curve which is defined in parametrically. Okay. That is, we just have to replace everything which is in terms of x and y, as we just have to do it. X must be substituted by the parametric equation which is given, that will be in terms of t. That is, everything which is in x, y, dx, dy, everything will be replaced by t and dt. So just recall or remember the formulas that we are using, and we can do the problem correspondingly. So next, let's see how we can solve a problem in which the curve is defined by an explicit function. Okay, so we are asked to evaluate integral over c xy dx plus x square dy, where c is given by y is equal to x cube and x is varying from -1 to 2. So this is not of the form g of xy or something. We have to evaluate the integral which is given to us. This is given to us as xy dx plus x square dy, and y is the curve is defined by an explicit function. So how we'll do, we'll replace everything in terms of x. In the previous problem we had to change everything into t and dt. Here we have to change everything into x and dx. Okay, so how will we do? We'll replace the value of y, integral over c xy dx plus x square dy will be x varying from -1 to 2. So integral -1 to 2, x into y will be replaced by x cube and dx remains as it is, and x square is as it is, and if y is x cube, what will be dy? Dy will be 3x square into dx. So we'll replace dy by 3x square dx, and this is same dx and dx, so you can add them because it is x raised to 4 and 3x raised to 4. So altogether we get 4x raised to 4 into dx, and we just have to integrate it. This is simple. It will be x raised to 5 by 5. So 4 by 5 x raised to 5 varying from -1 to 2. What will be the value? The value will be 132 by 5. So this is how we can substitute or find the integral when the curve is given or defined by an explicit function. So you can, I would like to make some notations clear. That is, if we are given any curve, we know that how are we finding the integral? In the beginning we had told that the curve is divided into many sub arcs. So if suppose the curve is defined as the if C is composed of two other smooth curves C1 and C2, okay, then integral over C g of xy ds, it's not it can be anything, ds or dx dy whatever, but integral over C can be written as integral over C1 g of xy ds plus integral over C2 g of xy ds. So suppose we are given any curve C, and if we can partition it into or divide it into smooth curves, and if C is the union of these smooth curves, so instead of calculating integral over C, we can calculate integral over each smooth curves individually and then just sum them. So mostly in application level, the formulas or the calculation will be done not of the form g of xy ds or dy. It will be like this: integral over c p of xy dx plus integral over c q of xy dy. Now we won't write it in separate sums, we write it together usually. That is integral over c p of xy dx plus q of xy dy. Just now we had seen an example, that is how we consider most of the problems in many application level will be of this form. So when we are asked to find the line integral, we just have to substitute the corresponding values. So we had seen the first example we had done, it was to find integral over c g of xy into dx, dy, ds and all. So these type of problems can also occur in that case. That is, we have to find integral over c p into dx plus q into dy, where c is defined parametrically also. So in that case, what we'll do, we'll replace p, q, dx, dy and all, everything in terms of t and dt, and solve the given integral. And there is one more notation that you should keep in mind when we have an integral over C with a circle over here. That means the C is a closed curve. Now we all know what is a closed curve. We had discussed in the first section, first lecture of this section. So when a line integral along a closed curve is often denoted by integral over C with a circle P dx plus Q dy. So that is a notation you must remember. Now you can see in example 3, we are asked to evaluate integral over C x dx, and there is a circle in this integral. So that means that is a closed, C is a closed curve. So we can see C is given to be the circle x equal to cos t, y is equal to sin t, where t varies from 0 to 2 pi. So how will we find? We will replace, variation of t is given to us. So we will replace x by cos t, and what will be dx? Dx is minus sin t. So integral over C x dx will be integral 0 to 2 pi cos t into minus sin t dt. Now this is cos t sin t. How you can use it by substitution method, which we had done in the first example, by substituting the value u is equal to cos t, then du will be minus sin t into dt. So this whole term will get cancelled. So we get the integral to be 1 by 2 cos square t from 0 to 2 pi. And what will be the value? Cos 2 pi is minus 1. So minus 1 square is 1. And cos 0 is 1. So 1 minus 1 is 0. So the integral is 0. So the integral of x dx over this circle is 0. So this is how we can do the various examples, or we can solve the problems by the formulas that we had discussed just now. Let us just remember these formulas once again. I'm just recalling them again. You can see it in the slide. If the curve is defined parametrically, then the integral over C g of xy dx will be integral a to b g of f of t comma g of t into f dash of t dt, and integral over C g of xy dy will be integral a to b g of f of t comma g of t into g dash of t dt, and integral over C g of xy ds will be integral a to b g of f of t comma g of t into root of f dash of t square plus g dash of t square into dt. Now if the curve is defined using an explicit function, say y is equal to f of x, where x is varying from a to b, then the integrals will be as follows. That is, integral over C g of x comma y dx will be equal to integral a to b g of x comma f of x dx, and integral over C g of xy dy will be equal to integral a to b g of x comma f of x into f dash of x dx. And finally the line integral with respect to arc length, that is integral over C g of xy ds will be equal to integral a to b g of x comma f of x into root of 1 plus f dash of x whole square into dx. So that is how we are going to do it. So just remember it. Remember these formulas, keep these formulas in mind, and do the corresponding problems. So that's it for today's session. Thank you. Stay home and stay safe.